Okay, so our last speaker of the day. I'm really pumped about this because turns out he is a master of WebGL. And as you all know by now, that is something I love dearly. We have the pleasure to have, last but not least here today at Nordic.js, Felix Palmer. Yeah.
Okay, thanks. That's going to be quite tough to follow as an act, so well done, guys. So my name's Felix. I've come from Prague, where I work as sort of independent software developer. I'm going to talk to you today about WebGL. So most of you, if you've seen WebGL before, probably think of something like this, some kind of big 3D application where to build something of this sort, you have to understand about 3D maths, lighting, physics, all this kind of stuff. And often, this is presented to you in the form of some kind of tool, like Three.js, which hides all this abstraction from you and just lets you build all this kind of stuff from like a kind of a high level standpoint, but without actually understanding the low-level stuff. So the kind of aim of this talk and some of the other talks that I've given is to kind of break it down a little bit and talk about what WebGL actually is. And to me, WebGL is not so much about 3D graphics. It's more about enabling you to use the second processor that you have in your machines, your mobile phones, from within your web browser. So it's enabling you to use your GPU. And often this can be in the form of 3D graphics, but it doesn't have to be. It's essentially a way that you can do computation on a GPU. Okay, so this talk is going to be split into multiple parts. The first bit is going to be like an overview of WebGL, kind of the minimum kind of basics of what you need to do to get WebGL working in your browser without a framework. So once we have this bit of background working, then I'm going to use this to build a Tetris game. Now, this is going to be a little bit different from building a Tetris game in JavaScript in that I'm going to store the actual state of the game board on the GPU, not within JavaScript. So this is a bit unusual, but it's going to demonstrate to you that you don't just have to use a graphics card for graphics. You can use it for other things as well. This approach in general is called general purpose GPU computing, or GPGPU for short. And it's been used in lots of different areas as graphics cards have got more and more powerful. And at the end, I'm just going to show you some quirks of working in this system, as well as a couple of demos. Okay. So WebGL basics. So there's sort of 6 high-level things that we need to do to get WebGL working in a browser. And I'm just going to go through these at a high level, and then I'm going to dive a little bit deeper into each one of these. So don't worry if you don't understand every single thing that I'm going on about here. It is quite complicated. It's quite a lot of stuff, especially if you haven't done graphics card programming before. But think of this more as kind of background. A lot of this stuff is sort of one-time setup that you do when you're making your application. But day in, day out, you're not really having to do this again and again and again. OK, so what are the steps? So first of all, we need to ask our browser for a canvas and get what's called a WebGL context from this. So this is just what I like to think of as our gateway to the GPU. This is something that we can call methods on, upload data, just get it to do whatever it is that we want to be doing. Once we have this context, then we need to describe to the GPU what it is that we're going to be drawing. Because at the moment, it's just a black screen. So first of all, we have to upload some sort of geometry to our GPU. And the simplest geometry we can draw is just a triangle. What we're actually going to be doing in the examples I have here is drawing 2 triangles that we're going to put together to form a square. And this is something called a quad. It's just basically 2 triangles, a square. So once we know what we're drawing, we have to describe how we're going to draw it. And this, for me, is the really interesting bit of WebGL, writing what's called shaders. These are actual programs that execute on your graphics card and let you do lots and lots of effects. And this is the stuff that I think is often hidden from you guys. Like, it's there, available on every web page, but you don't really get to see it because it's sort of many, many levels down in all the frameworks that are out there. So there's 2 types of shaders. The first is a vertex shader, and this is a program that will be executed on every vertex within your geometry. So this lets you position your shapes on the actual graphics card. The second program is called a fragment shader, and this is going to be executed on every pixel within your geometry. So this doesn't output position, this outputs color. So this describes how your shape is going to be drawn in terms of color. The fourth point I have here is just to kind of make it clear that these aren't some kind of crazy programs you compile offline and you have binaries that you attach. These are just strings. These programs, these shaders, they're sort of created in the browser and compiled in the browser and then uploaded to the graphics card. So you operate on them in the same way that you would any other string in JavaScript. OK, so at this point, you actually have something being drawn onto your screen. But to actually do interesting things with it, you need to pass some data in from JavaScript. You don't want to have to recompile your programs every time you want to do something different. So you have these sort of conduits into your program in the form of uniforms and attributes. So uniforms are types of variables which are defined globally across your entire scene. And attributes are types that are variables that are defined on a per vertex basis. OK, and then finally, the output is rendered into a canvas element, and you can do whatever you like with it. You can move this around your screen. You can transform it to CSS. OK, that probably felt like a bit of a sort of steam train hitting you in the face in terms of information. So I'm going to break it down a bit and see if I can get someone to stick some more. So creating a canvas element should be reasonably familiar to you if you've used JavaScript before. You can either have it in the page or just use it, create it using document create element. And once you have it attached in your web page, you just ask it for a WebGL context like this. Simple. So creating geometry, again, conceptually kind of simple, I think. You basically define a set of coordinates. So here, I'm defining two triangles. And there's always kind of pairs of coordinates. So this bottom vertex here, -1, -1, is defined by these first pair of numbers here, and so on. OK, so onto shaders. And again, this is the bit that I think is kind of really interesting. This is where you can do quite a lot of creative stuff. So I mentioned you can write two types of shaders, vertex shaders and fragment shaders. So first of all, vertex shaders. The structure of a vertex shader is basically this main function, which only has to do one thing, and that is to output this GL position variable. And what this GL position variable is the final position of your vertex. Now, at this point, if you're still awake, you may have noticed this isn't JavaScript. So what is this? So this language here is called GLSL, and it's what you use to write shaders. It's kind of like an extension of C. So if you're used to C-like languages, which JavaScript is one of, then this should be kind of vaguely familiar. But there are some extra features. So one thing is that it's typed. And a good example of this here is that you have the varying vec. So vec2 is a vector of two components. And if you've forgotten your kind of school maths lessons, then a vector is just a collection of numbers. So you can describe a position on the Earth's surface with two numbers. So that could be a vector of latitude and longitude. OK, so that's a vertex shader. What about a fragment shader? So again, we have a similar structure. We have a main function. But now, rather than outputting a vertex, we want to output a color. So again, we're outputting a vector, and it's 4 components. But here, rather than it being the position of our vertex, it's the color. So the first component is red, then we have green, then blue, and then alpha. So one thing I haven't mentioned on these two slides is this v coordinate here. And this is actually quite interesting and probably one of the most difficult concepts to grasp in GLSL because it's completely different to what you're used to from JavaScript. So this here is a special type of variable which you define in your vertex shader, and you pin it to a certain value on your model. And then as your shape is being drawn, then the graphics card automatically smooths between one value to another. And this essentially lets you have variables which change on a per fragment basis rather than on a per vertex basis, which is very, very useful. So to sort of see how this works, what I'm doing in the vertex shader is I'm basically just copying the value of A coordinate to V coordinate. So the values of V coordinate are just these numbers that you see on each vertex. And then when I'm drawing in the fragment shader, then the graphics card automatically smooths between these values for me. So here in the bottom left, it's going to be -1, -1. So both my red and my green channels are negative, so I don't see anything. And then as I move across the image to the right, then I'm getting more and more red growing in my image. So I get this kind of red gradient and green gradient across the whole image. OK, so to give a bit more detail on these data flows that I'm talking about, I just have this diagram here to show what you can pass from JavaScript and what you pass between the shaders. So the simplest one are just uniforms. These are passed from JavaScript into both your shaders. Then you have attributes, which let you associate data to your vertices. So this might be position or colors that you have on your vertices. And then you have these varyings, which you can kind of think of as smoothed out attributes, or something that was calculated from those attributes. OK, so to recap, to draw something with WebGL, we need to get a canvas, ask it for a WebGL context. Once we have that context, we upload what we're drawing, so in this case, a quad. Then we write two shaders, which describe how we're going to draw that thing. We compile these in the browser, and then we control them using uniforms and attributes. And finally, this is just rendered to our canvas element. OK, so now that you're all experts in WebGL, let's build something. And let's build something hard to make it even more fun. So here, what I'm going to be focusing on is writing fragment shaders. So programs which take some kind of input and output some kind of texture. So they're concerned with just drawing one pixel, and it's going to get executed across our whole texture, giving us some kind of pattern. So as I was mentioning earlier, when we write programs with WebGL, or a lot of the programs that are out there, then the kind of flow you see is something like this. You have some kind of JavaScript app, often very complex, which is taking in user input, manipulating state. And this then tells WebGL what to draw. But the key point is that here, JavaScript is actually holding all the interesting information about what it is that's going on in your program. WebGL and the screen are just used for kind of display. Now, what I'm going to want to do here is try something a bit more interesting, in my opinion, and shift some of this logic from JavaScript into WebGL, and see if we can do more of this kind of general purpose computation on the graphics card rather than doing it just in JavaScript. So when I was talking to you before about the kind of pipeline of setting up a canvas element and drawing to a screen, I was kind of lying. I was kind of implying that you did your WebGL rendering and it goes straight to your screen. That's all it's kind of used for. But you can actually do this quite interesting technique called rendered to texture, where rather than rendering to a screen directly, you just render to another texture. So this can be something that's off-screen, or you can just think of it as just a massive array of data, a two-dimensional array. And you can actually read this back from JavaScript. So if you wanted, you could have JavaScript, WebGL, JavaScript. It would be a bit stupid, but you could do it. So with this kind of pipeline, you can do some interesting things. For example, if you had a game, then you'd have your game engine in JavaScript. You'd render your 3D scene in the second chunk of this, in this WebGL here. And then you could draw on, I don't know, some kind of score on top of that with this kind of WebGL. So you can kind of composite your different layers in that way. But why kind of stop at this stage? We can go one step further with this rendered texture technique and actually set up a feedback loop that is purely on the GPU. So not just taking some states that we have on our JavaScript side and passing it through some processing stages on the graphics card. We can set up something that looks like this, where we initialize our system from JavaScript and then set up this kind of rendering loop or processing loop on WebGL, where we're basically having one program that outputs a texture that another program reads, and so on and so on. So you could use this for like a physics simulation or something like that, something that keeps track of some data. And at some point, you sort of pull that out and display it onto the screen so you actually have something. OK, so I want to use this kind of system to build a simple Tetris-like game, just to show you how it works. And there's not going to be too much code. I hope that you guys are going to be able to understand it, even if this has been quite abstract up until now. So what we're going to do is write a bunch of shaders. And each of these stages is going to be a shader which takes as input a texture and possibly some uniforms from JavaScript. And then it also outputs a single texture itself. So all of our state is being held in these textures. You don't have variables or this kind of nice stuff like objects in WebGL. You just have to put it into textures. The way we're going to do this is we're going to represent a game of Tetris like this. So if you think of this as a texture with each of these blocks being a pixel, then the black pixel is just going to be empty space. The red pixels are going to be moving blocks that are falling down, and green pixels are ones that are settled. And then our challenge is to write some programs which can initialize this kind of state and then transform it as time kind of moves on. So how are we going to do that? We're going to split what we're doing into a set of stages and then control them from JavaScript. So the first stage is this one here, the spawning stage, where we're basically going to create new blocks at the top of our screen, and we're also going to draw the green floor. And this stage knows nothing about moving things along. All it does is it takes the existing state of the game and adds a new block at the top. This is then going to pass its output to the shift stage, which does nothing but takes the red blocks and moves them down. It does nothing with the green blocks. This then gets passed on to solidify, which doesn't move anything, but it checks for if your red blocks are sitting on top of something green, and if so, changes them to green, which means they're now solid. And then finally, the copy stage does nothing but copies across this thing so we can use it in other places. So here you can see that I'm drawing out to the display, and these kind of red and blue arrows are just sort of saying that what we're going to do from within JavaScript is not have a spawn step every time. Sometimes we're going to spawn a new brick, but sometimes we're just going to go straight to shift, and that way make sure we don't have just too many blocks coming down. OK, so what do these shaders actually look like? So the first one is the spawn shader. And here what I'm going to do is draw the ground. So the first thing to look at is what I'm passing into this program. So the first thing is a texture. So this is the current state of the game. The second parameter is this varying vector UV. So this is something which changes across every pixel. And this is just telling us which of the pixels in this block we are. So for example, the one in the bottom here, unfortunately, you can't quite see. There's supposed to be a grid drawn there, but the resolution is not good enough. So the bottom pixel here is 0, 0, and the top one here is 1, 1. So this first line does nothing but just copies our texture in. It just looks up the current value and draws it out. And then to draw the ground, all we're going to do is just have this if condition, which looks at our position and says, OK, if we're below this line, then draw green. And this parameter step is just telling us kind of how far pixels are apart. So by comparing it to step, we're just saying just draw the first line in our shader. So to actually spawn something onto our stage is basically the same trick as drawing our ground, except we just use some slightly different logic. So I have this encapsulated in this should spawn function here, which does a bunch of comparisons between some position and some UV position within our texture. So all this function is doing is just picking out one pixel for us that we're going to draw. Now you should notice here that this x parameter here that I'm passing in is a constant. So this is always going to draw the same pixel in the top left. And that's not what we want. We want to have some way of randomly changing this on every frame. So you might ask, how do we do that? Now, there's no way of doing this directly within GLSL. You can't just say, give me a random number. It doesn't work like that. What you have to do instead is pass in a random number from JavaScript. And we do this by using this uniform up here. So on every frame, we're just going to update this and render. So this way, we can sort of put in slightly different data on every frame and tweak things from within our JavaScript world. So that's what we're doing here with x. We're just taking this urandom parameter and just converting it to be the right thing so it sort of fits onto our screen. OK, so now we know how to create blocks. What about shifting them? How do we transform the top image into the one below, where our red block has moved down one position? So here, what we need to do is do two texture lookups. So we have to kind of imagine that the program is sort of running in the context of this image here. So if I'm this block there, what I want to ask is the block above me red? And if it is, copy its value down. So we're basically going to do two texture lookups, the current value, the one that's above us, and then just shift only the red channel. So the effect of this is that the red blocks are going to move down, and the green ones are going to stay solid. And then finally, detecting the hits at the bottom. So it's more or less similar to what we're doing with shifting the blocks along, but rather than asking what's above me, we ask what's below me. And we have these two conditions. So one, am I alive? So am I red, basically? And is the one below me solid? So is the one below me green? And if that's the case, then we just swap the color from red to green. And this funny notation here is just kind of swapping the two color channels. OK, so what does this actually look like? So this is the actual game running. And I can zoom out and show you what the other textures are kind of doing in real time. So this one at the top here is the spawn step. So this is kind of a little bit jerky because it's not actually getting executed as often as the other steps. And if I slow it down a little bit, with this, yeah, that's easier to see. So then the second stage is the one that's actually moving our blocks. So this is taking the output from either our spawn step or the copy step that we had from before, and just shifting the blocks one by one. And the thing to notice here is as the red blocks hit the bottom, they don't instantly change, because this shader has no understanding of solidifying things. That happens in this shader here. So this is taking its input from the shift step and just checking if I've hit something green, make me green as well. And this has the effect of solidifying things. And then finally, we can have another shader, which is more kind of to make this basically look pretty, which just reads in the value of the board and just shows these blocks in a slightly more kind of presentable fashion. OK, so at this point, you might ask, why do this on the GPU? And the best answer is probably it's a good way to get invited to a conference. But on the other hand, it's kind of very parallel. So this kind of computation is something which, if you were doing it in JavaScript, yeah, you could do this as well. It's not hard. But if you wanted to scale this up to handle a much bigger sort of size of board, then you could easily make this be 1,000 by 1,000 pixels. This at the moment is 32 by 32. So it's processing maybe 1,000 entities, but you could make it 1,000,000. And it's no real problem to kind of just boost the simulation rate higher and not throttle the rendering at all. It just shoots up. It runs really quickly. Yeah. OK. So now I'd just like to talk about some things about coding on the GPU, which definitely weren't obvious to me when I got started. And this is just kind of more for sort of interest. But if you think a little bit about how graphics cards work compared to CPUs, it sort of makes sense that this is the way things have to be. So when our graphics card runs this kind of simulation here, it's not kind of iterating over the whole texture. It's processing these blocks in huge parallel chunks. So it might do a couple of hundred of these pixels in one go. And that's important because the only way the graphics card can make this work is if all these blocks run in lockstep, if all these threads that are processing every single pixel are taking the same amount of time. And this has some interesting consequences. So the first one is if you have some kind of branching in your code, where you make some kind of decision depending on what your input value is. So for example, you check if you're a block, and if you're a block, you do something different, some kind of expensive calculation that renders things nicely. And you might think this is going to optimize your code, because now only a couple of the pixels have to do this expensive calculation, and the rest just draw black. But it's not quite that simple, because what's actually going to happen is this. The graphics card is basically going to execute both the statements, both your if and your else block, and then just throw away one of the colors. So you won't get any optimization at all. Now, this isn't quite true. Like graphics cards vendors might do some clever tricks, and you can't quite know what they're doing. But this is what you have to assume. You don't really know if this is actually going to speed things up. And this kind of makes sense, because say you're drawing a block of 10 by 10 pixels, so 100 pixels, and only one of them needs to do this expensive calculation, then you can't have that one finishing slower than the other blocks. I mean, it has to all finish at the same time. Similarly, when you have loops, then they're not really loops, or you can't use them in the same way that you'd expect in JavaScript. So a big no-no, and this won't even compile, is trying to create a loop and have it iterate for an unknown number of iterations, which seems crazy. It seems like such a basic thing. But you can't do this on the graphics card. You can do it if that's a constant, but if you do some kind of lookup, then this is not going to work. And that's, again, for the same reason. You have this block of pixels, and some of them can't execute faster than the others. They all have to be as slow as each other, because that's the only way that you can kind of guarantee they're going to work. So to make this work, you can do something like this, which is a bit horrible, where you basically have a loop that executes 100 times, and then you break out early. Looks nice, seems to solve the problem, but it's still going to run slowly, because the graphics card is still going to stubbornly do every iteration of the loop for you, and then just throw away all those results, just so it can sort of remain coherent. OK, so that's all I have in terms of actual theory. I just want to show you some kind of more impressive examples of some of this in practice. So the first is a simulation of birds. So here I think there's about 1,000 birds. And each of these has got some kind of position that has been calculated and stored on the graphics card, and also some velocity. And then they have some kind of physics-like behavior which makes them fly. And you can control them slightly by sort of moving your mouse and getting them to sort of move away. But here, all that state of where each bird is being stored on the graphics card. If you had this on the JavaScript side, this wouldn't work. You just wouldn't be able to upload all this data fast enough to the graphics card to make it work. So that's why you have to do it on the graphics card directly. And the next example, I mentioned physics simulations before, and this kind of stuff is really great for that, is this sort of water effect, where you have lots of these particles, and as you move your mouse and disturb them, then you kind of get this nice sort of looking fluid, which is sadly a bit pixelated on the screen. But if you squint, maybe it looks nice. OK, so that's all I have. I hope that was somewhat informative and didn't hurt your brains too much. So yeah, if you want to come and talk to me about WebGL, I'll only be happy. Thanks.